In as complex domain as a fluidized bed, we need to make certain approximations in order to be able to have a reasonably simple model still containing the complexities of the problem. Now we have to, in an accurate, rigorous model of a fluidized bed, we have to take momentum, energy, and species conservation equations into consideration for a fully rigorous solution of the reaction problem in a fluidized bed. However, the demand of the computational demand can be very large, and there might be certain interactions that we can consider that are not pertinent to the problem that we are interested in. Therefore, we can just take those problems as stationary problems and leave outside our domain of interest, and we can solve our reactor design problem with limited applicability in certain cases, with reasonable accuracy in certain other cases. As such, we need to take this whole complex problem of flow around immersed objects, mass transfer through particles, mass transfer in and out of the particles, heat transfer through, in, and out of the particles, and generate a simplified model. How are we going to simplify this whole big problem? We are going to divide the fluidized bed into domains. First, within the bubbles, next, within the reactor. Now let's consider the bubble formation. I'm going to generate an enlarged domain of a gas distribution plate where we have particles being held up on that gas distribution plate, and our fluid gas, right? We said gas distribution, so let's continue with the gas flows through the perforations of the distribution plate or through the valves, depending upon the design, and that gas generates a bubble in which no particle survives. That our bubbles, gas bubbles, are forming around our gas distribution plate. Around that bubble, we're going to have a cloud of particles. Due to the momentum of the gas, we're going to have a slightly denser bubble domain here, depending upon the type of the particles, of course. And then we have domains of particles behaving like an emulsion. Now, how many phases did we create? We have created 3 different phases. One of the phases is the fluid phase, gas phase, bubble. The other phase is a relatively denser phase of cloud. The third phase is the bulk particle fluid mixed phase that behaves like an emulsion. So this is our first approximation. This is not, when we are talking about phase, we are not talking about like liquid, solid, gas phase. We are talking about an imaginary phase with almost imaginary boundaries. The bubbles will act like batch reactors. So once the bubble is formed, until it bursts, it is going to retain its chemical composition, provided that we have reaction between the contents and the environment. Let's put our symbolism of a batch reactor in the bubble. What is the design equation for a chemical reaction taking place, homogeneous chemical reaction taking place in a batch reactor? dNA over dt to be equal to Ra times V. Volume, right? If the volume is constant, now comes our second assumption, that our volume is going to remain constant. We're going to combine this term and this term, and we will write dCA over dt to be equal to R sub A. All right? Now this dt, this time, is going to refer to the lifetime of the bubble. If the bubble survives the progression of the fluids throughout the bed, that lifetime is related to the velocity of that bubble throughout the bed. So this time can be a space-time where we have the length that the bubble traverses divided by the linear velocity that the bubble has in the bed. So this is the first approximation. Now, through this batch reactor, we have mass transfer. We have mass transfer in the direction of going from the bubble to the cloud, and from the cloud to the emulsions. Let's see if we can create our bubble. All right, this is the gas cloud that we have treated as a batch reactor. It's the gas bubble, sorry. We have the cloud. And our A is being transported from the gas to the cloud by mass transfer. All right? So here we are going to take a concentration gradient. We're going to call this CA of the cloud, while we're going to define the concentration here as CA. B indicating bubble, C indicating cloud. Then we have here in the bulk CA of emulsion. And we're going to treat all those transports as simple convective transports of species. So between the cloud and the bubble, we have a mass flux that is represented by a mass transfer coefficient from bubble to cloud times the interfacial area between bubble and cloud times the concentration gradient. the flux between cloud and emulsion will be similarly so we are going to write our balance equations given these fluxes and given everything is operating under close to steady state conditions. So now in the simplified block diagram, we are representing bubble, cloud, and emulsion as different domains, different phases in the reactor, where we have a reaction and a mass transfer that is taking place, and we are considering all of that at constant temperature. We haven't introduced the effect of temperature into this problem yet. As I mentioned earlier, that we are going to treat the bubble as a batch reactor, where the reaction taking place in that batch is represented by a homogeneous model with a reaction rate constant K and the concentration of species A represented as Ca bubble. The component A is depleted in that batch reactor in two modes. Mode number one is a reaction, which we represent by minus K sub R times Cab, and the other mode is the mass transport. Here we are writing this in the opposite direction of the flux, that when we are treating this whole reactor, this is going to come as a negative term. So I'm going to write this expression as minus dCA over dt, and this time can be the clock time or the space time, which is represented by the relative velocity of the bubble and the length that it traverses as K times KR times Ca plus K bubble to cloud, A bubble to cloud times this time Ca bubble minus Ca cloud. I'm going to represent this in order to just follow things easily as KBC prime in one lumped parameter. The second domain is the cloud domain, and the cloud domain is going to be considered to be operating at steady state. What will happen in the cloud domain would be two things. One, the transport of species A from bubble to the cloud by this transport term, a reaction term, and another transport term from cloud to the emulsion. So we no longer have the unsteady state term in the cloud. We're going to treat cloud as a CSTR, a well-mixed reactor, intaking species A from the bubble through this transport term and transferring species A to the emulsion term through another transport term. In other words, we are going to write the species conservation balance for a CSTR under steady state conditions. This was the bubble. For the cloud, our balance will be pretty much the same. Let me write FA in minus FA out plus RA times V to remember what it was for a CSTR. Now instead of advective flux, we have convective flux coming from the bubble, going from the bubble, going to the emulsion, and the rate that is taking place in the cloud. So, coming from the bubble, KBC prime times CA bubble minus CA cloud going to the emulsion minus K prime cloud to emulsion CA cloud minus CA emulsion plus RA times V minus KR times CA. I will put the prime here to indicate that the V term is also taken into consideration and my balance equation is dimensionally consistent. So this is my balance equation for the cloud. As an exercise, write the balance equation for the emulsion. And after you finish, you will be exposed to the composite resistance that is due to mass transfer and reactions in the simplified model that are due to Kunoy and Levenspiel. Here on the board, we are going to look at the derived composite resistance, which is labeled as capital K sub F, which has all the components of mass transfer and a reaction into consideration. Now this composite system of the bubble, cloud, and emulsion, they all act like well-mixed reactors with their corresponding rates in the mixed flow domain. And then we have a film mass transfer equivalent of the transport between the bubble and the cloud and the emulsion. And those mass transfer terms are going to represent our fluxes in and out of that imaginary domains. They're all connected in series. As a result, we are going to have a composite resistance of the parallel series domain that are compounded by the fraction of the domain. So this is the fraction, relative fraction of the bubble domain. This is the relative fraction of the cloud domain, and this is the relative fraction of the emulsion domain. So this is going to take the volume parameter into consideration, and here we have the transport terms, mass transfer terms between bubble and cloud, between cloud and the emulsion. At the end, we have a lumped parameter for the mass transfer and the reaction. And since our reaction is a first order reaction, our transport processes are first order processes, we were able to lump them into a simplified term that is like a pseudo-homogeneous reaction term. Now there are correlations available and in our textbook that is going to allow us to calculate the relative fractions of the domains, that are going to allow us to estimate the mass transfer coefficients, and at the outset, before making any experiments, before making any measurements, we will be able to estimate a lumped kinetic term, which is called K sub f, that will represent our overall process in terms of a first order behavior. So what we have done, we have taken a very complex situation that needs the momentum, heat, and mass transfer problems to be simultaneously solved. We eliminated the heat transfer problem by assuming isothermal conditions. We have included the mass transfer problem as a convective mass transfer between three hypothetical domains. Gas domain is a little bit more real than the cloud and emulsion phases. And we have estimated mass transfer coefficients between those domains. We have lumped the transport processes with the kinetic processes, and at the end we obtained an expression that is valid for an ideal batch reactor or an ideal plug flow reactor. Remember that time could be a space-time represented by the position and the velocity. We can write this expression equally well as minus dCA over dZ. Z is the direction of the flow times U sub Z, and that is the linear velocity of the bubble in the Z direction. So, what have we designed? We have designed a fluidized bed reactor, and we have lumped sum the problems, and we generated a pseudo-homogeneous solution. Now, of course, you are going to be the engineer. You are the engineer. And the solution rests upon you. You may choose to derive the expressions through the correlations available in the literature. Most of them are textbook contents. Or you may wish to perform your own experiment and obtain your own pseudo-homogeneous kinetic parameter K sub f. Of course, performing this experiment has to represent your eventually scaled up reactor. In other words, the accuracy of your design will depend on your accuracy of your design parameters, even if you have modeled the system through correlations, through rate expressions that are available to you through literature. It is better to have a pilot scale unit constructed where you have estimated your own parameters, your own pseudo-homogeneous kinetic expressions, and then scaled your reactor up with the either justified design parameters or corrected design parameters. In this part, we are going to discuss an industrial problem of fluid catalytic cracking reactors that are very common in petroleum refineries. Now, fluidized catalytic cracking reactions take place on zeolite catalysts, and the reactions are highly endothermic. The cracking reaction, breaking carbon-carbon bond and substituting the empty bond with a double bond or with a hydrogen atom coming from cracked product or steam available in the reactor is highly endothermic. As a result, it needs a huge amount of energy transfer to the reactor. However, heat transfer rates are not affordable in the rates that the reactions take place. As a result, we need to provide energy into this reactor in a rate that is sufficient to compensate for the energy required by the reaction. So how are we going to do that? Well, the solution is in the fluidized bed reactor, which I will just try to symbolically draw here. That we have a riser. The riser takes in our fluid. Our fluid is heavy vacuum gas oil, which entrains the solid catalyst. Here our catalyst is hot, and that is the trick of the FCC reactor. The hot catalyst is entrained in the reactor zone we call the riser, and the reaction is pretty much complete in the riser within seconds. So both of them enter into the reactor domain, and into the reactor we also supply some steam. The function of the steam is twofold. One of them is to substitute for the protons that are used, protons of the catalyst that are used in the riser, and provide additional reactive domain in the domain we call the stripper. And in the stripper, of course, the catalyst part, the fluid that surrounds the catalyst particle is also stripped. This is referring to the same operation as we use this term in the distillation columns. So it also steam strips the surface of the catalyst. So we have a fluid phase, that is going to be also sent cracked fluid phase, but this fluid phase has to be separated from the solids in a cyclone. Okay, we take the solids, fluids are sent to the distillation operation. We take the solids. What we have on the solids is a carbon layer which is deliberately, intentionally left on the catalyst, a carbon-coated catalyst, which is sent to another fluidized bed where we have this time air plus steam, depending upon the design, of the reactor, we have catalyst particles that are being oxidized. We have carbon dioxide, steam, excess oxygen, nitrogen, leaving the oxidation reactor. And then we have particles. Let's take the particles from here that now have the energy of combustion that they can carry as their high temperature bulk. So the catalyst is both cleaned up of the coke is eliminated, but it is also at a temperature that is going to drive the reaction forward. So now I'm going to take this description and we'll simplify this into two block diagrams. Let's see if our pen is working. All right. So we have two domains. Now instead of figures representing the real situation, I'm going to draw simplified diagrams. We have the reactor domain here, reaction domain here. We have regeneration domain here. Regeneration not only regenerates the catalyst in terms of its coke, but it also brings in the additional heat. Okay, so from the reactor, we have particles flowing to the regenerator. It is this stream. This is the particles. And from the regenerator, the particles are moving back to the reactor. Right? So we have a steady state condition as far as this reactor is concerned. The particle flux in either direction, if the number of particles going in either direction are the same, then we have a steady state condition of an particle reactor and an particle regenerator. Of course, we have vacuum gas oil entering this reactor. We have reaction products leaving the reactor. We have air entering this reactor. And we have combustion products. These are reaction products. We have combustion products leaving the reaction. What are different is that our particles here are at T1, our particles here are at T2. Both of the reactors are operating adiabatically. In other words, the net heat is 0. Net heat is 0, but we have combustion reaction here, cracking reaction here. The energy exchange due to the reaction plays a significant role in eventually determining the steady state temperature in those reactors. So what did I do? I simplified a complex reaction network, reactor network, a complex reactor network, into two block diagrams. And in those block diagrams, in addition to fluid domain entering and leaving, we also have solid domain entering and leaving, but we can treat this domain as a pseudo-homogeneous reactor. We can treat this domain as another pseudo-homogeneous reactor, and we can estimate very quickly the needed materials and needed energy transport, and we can adjust the flow of the incoming and outgoing streams. Of course, if we need a little bit more accurate understanding, we have to understand the residence time distribution of the fluids and solids in these domains. A better representation requires a knowledge of sorry about the squeaky sound, knowledge of residence time distributions. All right, beautiful experiments are published in the literature, and we will discuss those problems as in-class exercises that you have sometimes radioactive tracers, and we can develop the profiles of particle, velocity profiles of the particles through methods like X-ray tomography.